Hello, my name is Destiny Williams, and I am a chemical engineering PhD student at Oklahoma State University in Stillwater, Oklahoma. My advisor is Dr. Shori Hamadi. She's with the School of Chemical Engineering, and her collaborator, Dr. James May, is with the School of Materials Science and Engineering. Today I'm going to be presenting over continuous millifluidic surface modification of synthesized silver nanowires. The outline here, we're going to go over background, experimental procedure, results, and the conclusion and future direction. Some background information here. We chose the polyol process. We have ethylene glycol as the reducing agent as well as the solvent. Silver nitrate is our metal precursor. We want to make silver nanowires, so we chose silver nitrate. Copper chloride is the salt mediator. There's a schematic of salt mediating happening here between copper chloride, ethylene glycol, and the silver ion. PVP is the capping agent for this reaction, and in the event of a batch synthesis, you need argon gas as the purging gas. So that is the polyol process for synthesizing silver nanowires. So we chose silver for the nanowires because silver has high thermal and electrical conductivity, great transparency and mechanical flexibility, and it's relatively easy and economical to synthesize. So that's why we chose silver. Some issues that we have with silver is that it is chemically unstable, it is prone to oxidation. Whenever that occurs, our end goal is to use this for transparent conductive films, and with that it raises the sheet's resistance, and that's not something we want. So the whole purpose of this talk here is to discuss the continuous surface modification, and the surface modification is how we're actually stabilizing our silver nanowires. So for the synthesis portion, how we actually make the silver nanowires, there were two options, batch or millifluidic. We went with millifluidic for a few reasons. Millifluidic has a controlled reagent addition, so it is controlled by a peristaltic pump, as you can see here in this diagram. Additionally, it's a closed reaction environment. So we have the reaction occurring inside of PTEF tubing, and that is submerged in a silicone oil bath, and then the product is collected. With batch synthesis, you have an open reaction environment happening in a 50 milliliter round flask, or just a round flask in general, submerged in a silicone oil bath. For the difference between the two with respect to the nanomaterials created, in a millifluidic synthesis, it favors nanowire morphology due to the reactor environment. Batch synthesis, you're going to get a lot of nanoparticles mixed in with your nanowires. So you don't have a majority nanowires, you have kind of a healthy mixture of everything happening. It's such a large reaction environment. So we went with the millifluidic synthesis. This is a picture of the setup of a millifluidic reactor, and these are three identical reactors set up here. You can see the peristaltic pump in the background there. Here's the outlet of one of the reactors, and of course the inlet has the syringes with reagents hooked up to it. And PTF tubing coiled around and is submerged in the silicone oil. So once we've synthesized the silver nanowires, our end goal is to make this entire process continuous, from synthesizing the silver nanowires all the way up to the surface modification. So in order to do that, we're going to stepwise the process. We're going to start with the batch surface modification. So we created the silver nanowires. After we synthesized them, we did a acetone wash with 2 DI water washes, and then centrifuged the samples after each wash. And then we took that, which is in a DI water solution, so now it's an aqueous silver nanowire solution, and we added them to a 50 milliliter round flask. We added PVP as a stabilizing agent, ascorbic acid as a reducing agent, and sodium hydroxide to control the pH. We selected palladium as our surface modifier. Palladium undergoes a galvanic reaction, and it replaces silver on the surface of the nanowire. So palladium is deposited and silver is released. We chose palladium just because there have been studies shown that palladium is good at this galvanic process. So we did it with batch, and we proved we could do it with batch. And there are pictures in the results section. Again, just another picture here of our setup in our lab. This is with the batch surface modification when our silver nanowires were in an aqueous solution. This dark color is what we're looking for at the end of a reaction. The reactions take about 4.5 hours for the entire surface modification to be completed. So that's what's going on here in this picture. You can see the tubing from the peristaltic pump and the syringe attached to it. Once we were able to prove that we could do this with a batch process, the question we had to kind of next step would be semi-continuous. Can we get the silver nanowires or keep them in a ethylene glycol solution versus the acetone wash, the 2DI water washes, and centrifuge? Can we just keep them in that ethylene glycol solution and then see if palladium will deposit on the surface? So that's what the purpose of the semi-continuous surface modification was. So you have your reagents, you have the synthesis of your silver nanowires being fed into a 50 milliliter round flask. Inside of that flask is an aqueous solution of PVP sodium hydroxide and ascorbic acid. So then you have your palladium precursor that is controlled by a peristaltic pump, and both of these things are being added dropwise, and this is under rigorous stirring. The batch was under rigorous stirring as well as the semi-continuous. Once this proceeded, we did imaging for the samples and found palladium was deposited on the surface. So this was excellent. This is great news for us. We were still able to achieve that palladium galvanic reaction between palladium and silver with these wires. This is the picture of the setup from our lab. You have your millifluidic reactor here, reagents for the synthesis of the silver nanowires, this 50 milliliter round flask where both palladium and the silver nanowires are being deposited into. Judging by the color of this was at the very beginning of an experiment. I say very beginning, it's a 4.5 hour long process, near the beginning of this process. So rigorous stirring, adding both in at the same time, we were still able to get palladium deposited on the surface. So now considering the next step for us. So we have accomplished this in a batch process. We've accomplished it with semi-continuous. Now we want to tackle the continuous. Can we do this without that 50 milliliter round flask and stirring? So a major difference here, obviously, is that there's not a flask. It's all connected with tubing, but there is a ice bath at the outlet of the millifluidic reactor. Notice in this schematic, there is no ice bath. That is because the round flask is open to atmosphere. It is not insulated. None of the tubing is insulated, and that fluid is being dropped in at 40 microliters per minute. And so we made the assumption that because of that slow flow rate and that majority of liquid already in that round flask under rigorous stirring, that heat is going to dissipate quickly and attain those room temperature of like the room, 20 degrees Celsius. So that's a difference here, that we no longer have stirring, we have a shorter length of tubing coming out and then into surface modification, so we needed to quench or cool down that outlet stream. So that's an addition that we're going to have to account for here. Once those quenched silver nanowires come out, they're going to undergo this surface modification, and we're going to achieve that with just a T-junction with our tubing. And we're going to have a peristaltic pump adding in the palladium precursor as well as a reducing agent, ascorbic acid. So once all of those are added together, we're going to collect the product. You see here there's another set of coils here. So we're going to actually, because we have to account for that 4.5 hour surface modification time. So we're just going to be able to use that residence time or reaction time to calculate the length of tubing there. And then collect the sample, and hopefully we see palladium deposited on the surface of the nanowires. So this is our end goal. We are working towards this, and we're very close to achieving this. So now the results section. The first couple of slides here in results are actually from papers that my advisor wrote. And this is comparing the batch and the millifluidic reactor. So as I mentioned earlier, Batch and millifluidic are different because batch creates all kinds of nanoparticles, where millifluidic really favors nanowire morphology. So with batch, you can see here with these 6 samples, these are 6 different reactions. These photos were taken from 6 different samples, and none of them look the same. So an issue with batch is reproducibility, repeatability of the experiment. Can we get the same results? We can't, because it's such a large reaction environment. So when we look at millifluidic, again, these 4 samples are from 4 completely different reactions, and the nanowire morphology is there. They all look very similar. And what's also really cool about these samples, as you notice, they go from 120 degrees Celsius to 150. So that means that we don't have to run the experiment at this high 150 degrees Celsius. We can get nanowires as low as 120 degrees Celsius. So that's another attractive quality about millifluidic synthesis. So now, again, this is from a paper my advisor published. We're looking at UV-Vis and we're looking at EDS to verify that we've made nanowires, additionally that we have made silver nanowires. So these images concentrate in on very dense part of the wire here, and from that dense part of the wire, this peak in this kind of 3.25 to like 3.5 kilo electron volt range corresponds to silver. So we are verifying we've made silver nanowires here. This UV-Vis just says, hey, yeah, we made some wires at 1.6 absorption, and then that 400 or around 400 nanometer wavelength. So now looking here at these 3 samples, the first sample is not modified. It's just straight up silver nanowires. Then you look at the next 2 samples. The only difference between the 2, the one in the middle has no sodium hydroxide added, and the one on the right has 0.025 grams of sodium hydroxide added. Visually, they're different because one has sodium hydroxide in it. It looks a little bit textured. There's a lot of good studies that say that a higher pH is better for withstanding oxidation. So now looking at, and that last sample is from the batch reactor, as you can see. Now looking at the semi-continuous, this was the silver nanowires in ethylene glycol solution. So bare silver nanowires, and then the next 2 are just like closer up. And this was with 0.025 grams of sodium hydroxide in both of these samples. It came from the same batch. So looking at the surface here, we've got some nice dark spots there, and that's confirming that we have deposited palladium on the surface through that galvanic reaction. So this was all really great news to us. Future experiments and improvements. So we want to connect everything, and we also want to take we want to swap out ascorbic acid with brown sugar to make it a green process. So now we want brown sugar to be our reducing agent. So we're connecting the 2 processes. We're going to use a different reducing agent to make it green, and then we're going to feed them into a 3D printer to make the transparent conductive films. This is where Dr. Smay comes in. This is how we collaborated with him. He built a 3D printer for us and has delivered it to our lab. And here's a picture of that. It's in the batch phase right now. So this syringe is just, we can do this with batch processes. We're kind of playing with it with silicone right now, just to kind of see what we can make with it and get good training on it. But eventually we're going to be able to put our silver nanowires in a rheological substrate and then print transparent conductive films. And the end goal is to connect all 3 processes: synthesizing, surface modification, and the 3D print. References used for this discussion: the acknowledgements to my advisor, Dr. Hamadi, and as well as her collaborator, Dr. Smay, the Oklahoma State Chemical Engineering Department, the College of Engineering, Architecture, and Technology, and of course the National Science Foundation that has funded our project. I'm Destiny Williams, and thank you so much for coming to this talk. We will be standing by to answer your questions.